Welcome everyone to our first screencast on contextual word representations. My goal here is to give you an overview for this unit and also give you a sense for the conceptual landscape. Let's start with the associated materials. You might think that the name of the game for this unit is to get you to the point where you can work productively with this notebook called fine-tuning, which shows you how to fine-tune contextual word representations for classification problems. I think that could be a very powerful mode for you as you work on the current assignment and bake-off. For background and intuitions, I highly recommend this paper by Noah Smith. The beating heart of this unit is really the transformer architecture, which was introduced by Vaswani et al. 2017 in a paper called Attention is All You Need. It's a highly readable paper, but I recommend that if you want to read it, you instead read Sasha Rush's outstanding contribution, The Annotated Transformer. What this does is literally reproduce the text of Vaswani et al. 2017 with PyTorch code woven in, culminating in a complete implementation of the transformer as applied to problems in machine translation. This is a wonderful contribution in the sense that to the extent that there are points of unclarity or uncertainty in the original text, they're fully resolved by Sasha's code. And of course, this can give you a really good example of how to do efficient and effective implementation of model architectures like this using PyTorch. In practical terms, we're going to make extensive use of the Hugging Face Transformers library, which has really opened up access to a wide range of pre-trained transformer models. It's very exciting and it's enabled lots of new things. For us, the central architecture will be BERT. We'll have a separate screencast on that. And we're also going to have a screencast on Roberta, which is robustly optimized BERT. I think it's an interesting perspective in the sense that they explored more deeply some of the open questions from the original BERT paper. And they also released very powerful pre-trained parameters that you could, again, use in the context of your own fine-tuning. And then for a slightly different perspective on these transformers, we're going to look at the Electra architecture, which came from Kevin Clark and colleagues at Stanford and Google. I really like this as a new perspective. There are, of course, many different modes of using the transformer at this point. I'm going to mention a few at the end of the screencast. And just for the sake of time, I've decided to focus on Electra, and you can explore the others in your own research. Let's begin with some intuitions, and I'd like to begin with a linguistic intuition, which has to do with word representations and how they should be shaped by the context. Let's focus on the English verb break. We have a simple example, the vase broke, which means it shattered to pieces. Here's a superficially similar sentence, dawn broke. Now the sense of break is something more like begin. The news broke, again, a simple intransitive sentence, but now the verb break means something more like publish or appear or become known. Sandy broke the world record. This is a transitive use of the verb break, and it means like surpass a previous level. Sandy broke the law is another transitive use, but now it means Sandy transgressed. The burglar broke into the house is a physical act of transgression on a space. The newscaster broke into the movie broadcast is a sense that is more like interrupt. And we have idioms like break even, which means we neither gained nor lost money. And this is just a few of the many ways that the verb break can be used in English. How many senses are at work here? It's very hard to say. It could be 1, it could be 2, it could be 10. It's very hard to delimit word senses, but it is very clear from this data that our sense for the verb break is being shaped by the immediate linguistic context. Here are a few additional examples. We have things like flat tire, flat beer, flat note, flat surface. It's clear that there is a conceptual core running through all of these uses, but it's also true that a flat tire is a very different sense for flat than we get from flat note or flat surface. We have something similar for throw a party, throw a fight, throw a ball, throw a fit. We have a mixture of what you might call literal and metaphorical here, but again, a kind of common core that we're drawing on. But the bottom line is that the sense for throw in this case is very different depending on what kind of linguistic context it's in. And we can extend this to things that seem to turn more on world knowledge. So if you have something like a crane caught a fish, we have a sense that the crane here is a bird. Whereas if we have a crane picked up the steel beam, we have a sense that it's a piece of equipment. This seems like something that's guided by our understanding of birds and equipment and fish and beams. And when we have relatively unbiased sentences like I saw a crane, we're kind of left guessing about which object is involved, the bird or the machine. And we can extend this past world knowledge into things that are more like discourse understanding. So if you have a sentence like, are there typos? I didn't see any. The sense of any here, we have a feeling that something is elided, but probably localized on any, and any here means any typos as a result of the preceding linguistic context. Are there any bookstores downtown? I didn't see any. Same second sentence, but now the sense of any is probably going to be something more like bookstores as a result of the discourse context that it appears in. So all of this is just showing how much individual linguistic units can be shaped by context. Linguists know this deeply. This is a primary thing that linguists try to get a grip on. And I think it's a wonderful point of connection between what linguists do and the way we're representing examples in NLP using contextual models. This is a very exciting development for me as a linguist as well as an NLPer. Here's another set of intuitions that's related more to things like model architecture and what you might call inductive biases for different model designs. Let's start up here in the left. This is a high bias model in the sense that it makes a lot of a priori decisions about how we will represent our examples. The idea is that we have 3 tokens which we look up in a fixed embedding space, and then we have decided to summarize those embeddings by simply summing them together to get a representation for the entire example. Very few of these components are learned as part of our problem. We've made most of the decisions ahead of time. As we've seen, as we move to a recurrent neural network, we relax some of those assumptions. We're still going to look up words in a fixed embedding space, but now instead of deciding that we know the proper way to combine them is with summation, we're going to learn from our data a very complicated function for combining them. And that will presumably allow us to be more responsive, that is less biased about what the data are likely to look like. The tree structured architecture down here is an interesting mixture of these ideas. It's like the recurrent neural network. Instead of assuming that I can process the data left to right, the data get processed into constituents, like the rock as a constituent as excluded from rules over here. Now, this is probably going to be very powerful if we're correct that the language data are structured according to these constituents, because it will give us a boost in terms of learning. It could be counterproductive, though, to the extent that that constituent structure is wrong. And I think that's showing that biases that we impose at the level of our architectures can be helpful as well as a hindrance, depending on how they align with the data-driven problem that we're trying to solve. In the bottom right here, I have the least biased model in all these senses of all the ones depicted here. I've got a recurrent neural network like this one, except now I'm assuming that information can flow bidirectionally, so no longer a presumption of left to right. And in addition, I've added these attention mechanisms, which we'll talk a lot about in this unit, but essentially think of them as ways of creating special connections between all of the hidden units. And the idea here is that we would let the data tell us how to weight all of these various connections and in turn represent our examples. We're making very few decisions ahead of time about what kind of connections could be made, and instead just listening to the data and the learning process. And we are at this point on the road toward the transformer, which is a kind of extreme case of connecting everything with everything else and then allowing the data to tell us how to weight all of those various connections. And that does bring us to this notion of attention, which we've not discussed before, but I think I can introduce the concepts and a bit of the math, and then we'll see them again throughout this unit. So let's start with a simple sentiment example and imagine we're dealing with a recurrent neural network classifier. Our example is really not so good, and we're going to fit the classifier traditionally on top of this final hidden state over here. But we might worry about doing that by the time we've gotten to this final state, the contribution of these earlier words, which are clearly important linguistically, might be sort of forgotten or overly diffuse. So attention mechanisms would be a way for us to bring that information back in and infuse this representation HC with some of those previous important connections. So here's how we do that. We're going to first have some attention scores, which are simply dot products of our target vector with all the preceding hidden states. So that gives us a vector of scores, which are traditionally softmax normalized. And then what we do is create a context vector by weighting each of the previous hidden states by its attention weight, and then taking the average of those to give us the context vector K. And then we're going to have this special layer here, which concatenates K with our previous final hidden state and feeds that through this layer of learned parameters and a nonlinearity to give us this new hidden representation H tilde. And it is H tilde that is finally the input to our softmax classifier. Whereas before we would have simply directly input HC up here, we now input this more refined version that is drawing on all of these attention connections that we created with these mechanisms. And again, as you'll see, the transformer does this all over the place with all of its representations at various points in its computations. Here's another guiding idea that really shapes how these models work. I've called this word pieces. And we've seen this before. These models typically do not tokenize data in the way that we might expect. I've loaded in a BERT tokenizer, and you can see that for a sentence like this isn't too surprising. The result is some pretty familiar tokens by and large. But when I feed in something like encode me, the intuitive word encode is split apart into two word pieces. And clearly we're kind of implicitly assuming that the model, because it's contextual, can figure out that these pieces are in some conceptual sense one word. And you might extend that up to idioms like out of this world, where we treat them as a bunch of distinct tokens, but we might hope the model can learn that there's an idiomatic unity to that phrase. And this also has the side advantage that for unknown tokens like snuffleupagus, it can break them apart into familiar pieces, and we at least have a hope of getting a sensible representation for that out of vocabulary item. The result of all this is that these models can get away with having very small vocabularies precisely because we are relying on them implicitly to be truly contextual. Here's another inspiring idea that we've not encountered before. This is called positional encoding. And it's another way in which we can capture sensitivity of words to their context. So as you'll see, when you go all the way down inside the transformer architecture, you do have a traditional static embedding of the sort we discussed in the first unit for this course. Those are in light gray here, fixed representations for the words. However, in the context of a model like BERT, what we traditionally think of as its embedding representation is actually a combination of that fixed embedding and a separate embedding space called the positional embedding, where we have learned representations for each position in a sequence. This has the intriguing property that one and the same word like the will have a different embedding in this sense of the green representation here, depending on where it appears in your sequence. So right from the get-go, we have a notion of context sensitivity, even before we've started to connect things in all sorts of interesting ways. Now let's move to some current issues and efforts, some high-level things that you might think about as you work through this unit. This is a really nice graph from the Electra paper from Clark et al. Along the x-axis here, we have floating point operations, which you could think of as a kind of basic measure of compute resources needed to create these representations. And along the y-axis, we have glue score. So that's like a standard NLU benchmark. And the point of this plot here is that we're reaching kind of diminishing returns. So we had rapid increases from GLOVE, GPT, and up through to BERT, where we're really doing much better on these glue scores. We're increasing the floating point operations, but it seems to be commensurate with how we're doing on the benchmark. But now with these larger models like ExcelNet and Roberta, it's arguably the case that we're reaching diminishing returns. Roberta involves more than 3,000 times the floating point operations of GLOVE, but it's not that much better along this y-axis than some of its simpler variants like BERT-based. And so this is something we should think about when we think about the costs in terms of money and in the environment and energy and so forth when we think about developing these large models. Right, and here's a really extreme case. Who knows how long we can train these things or how much benefit we'll get when we do so. But at a certain point, we're likely to incur costs that are larger than any gains that we can justify on the problems we're trying to solve. And that kind of does lead us to this lovely paper, which talks about the environmental footprint of training these really big models. And it just shows that like training a big transformer from scratch really incurs a large environmental cost. That's certainly something we should have in mind as we think about using these models. For me, it's a complicated question, though, because it's offset by the fact that by and large, all of us aren't training these from scratch, but rather benefiting from publicly available pre-trained representations. So while the pre-training for that one version had a large environmental cost, it feels like it's kind of offset by the fact that a lot of us are benefiting from it. And it might be that in aggregate, this is less environmentally costly than the old days when all of us always trained all of our models literally from scratch. I just don't know how to do the calculations here, but I do know that increased access has been empowering and is likely offsetting some of the costs. And a lot of that is due to the contributions of the Hugging Face library. There are a lot of efforts along these same lines to make BERT smaller by compressing it, literally fewer dimensions, and other kinds of simplifications of the training process and BERT distillation and so forth. Here are two outstanding contributions, kind of compendiums of lots of different ideas in this space. And I also highly recommend this lovely paper called A Primer on Bertology, which explores a lot of different aspects of what we know about BERT and how it works, various variations people have tried, various things that people have done to probe these models and understand their learning dynamics and so forth and so on. It's a very rich contribution, certainly can be a resource for you as you think about these models. And just because we don't have time to cover them all, there are a bunch of interesting transformer variants that we will not be able to discuss in detail. I thought I'd mention them here. SBERT is an attempt to develop sentence-level representations from BERT that are particularly good at finding which sentences are similar to which other sentences according to cosine similarity. I think that could be a powerful mode of thinking about these representations and also of practical utility if you need to find which sentences are similar to which others. You have probably heard of GPT, the generative pre-trained transformer, in various of its forms. You can get GPT-2 from Hugging Face and you have unfettered access to it. And of course, there's more restricted access at this point to GPT-3. These are conditional language models, so quite different from BERT, and they might be better than BERT for things like truly conditional language generation. XLNet is an attempt to bring in much more context into these models. It stands for extra long transformer. So if you need to process long sequences, this might be a good choice. And this is also an attempt to bring in some of the benefits of conditional language models into a mode that is more bidirectional the way BERT is. T5 is another conditional language mode, as is BART. These models might be better choices for you if you need to actually generate language, where I think the standard wisdom is that models like BERT and Roberta are better if you simply need good representations for fine-tuning on a classification problem, for example. More models will appear every day, and I think it's worth trying to stay up to speed on the various developments in this space, because this is probably just the tip of the iceberg here.